let us start this lecture with a thought process. Identify your unique talents and set fire to your talents for serving mankind. In the last lecture, we basically derived various relationships for one dimensional combustion wave. In the process, we derived two important relationships. One is the Rankine relationship, other is Rankine-Huguenot relationship. And we will be using those relationships and trying to understand the various regimes of the deflagration and detonation. In other words, when the detonation can occur, when the deflagration will occur, that we will be discussing about. So, let us now invoke basically the Rankine-Huguenot relationship. If you recall that we had derived this Rankine-Huguenot relationship, this is Q is equal to gamma minus 1 P2 by rho 2 minus P1 by rho 2 of P2 minus P1 into 1 minus rho 1 plus 1 minus rho 2, and this is basically the Rankine-Huguenot relation. And if you look at, if I take this Q as 0, right, for example, if I take and if I plot this P2 versus the 1 over rho 2 for a particular P1 and rho 1, right, I will get a relationship like this, that is I am plotting P2 1 over rho 2 and for a particular P1 and rho 1, right. So, you will get a relationship, and this is for a particular this is your basically P1 and 1 over rho 1, this is this region, and this is Q corresponding to Q is equal to 0, and this is corresponding to normal shock wave, because this is one dimensional, so therefore it is corresponding to one side. But if it is Q is greater than 0, that means some finite value, then naturally what will happen? There will be another curve will be coming. Now, if I consider this as my initial point, then it will be like this. This is my initial points. So, what will happen? Let us see, and this will be and I can consider this as a this is the point. I can say this is basically A and this is your B, and this region is goes towards very high values, right, this goes towards infinity kind of things. If I consider this case as A and B, right, and there will be other regions. Let us now invoke our relationship what we had derived for the velocity, right, V1 square, we know that is nothing but a P2 minus P1 rho 1 minus rho 1 by rho 2, isn't it? This is the one we derived, right. Now, if I consider this as a P1 and this is also, this correspond to P2. So, P1 and P2 is same, is not it? At the point B, at point B what is happening? At point B what is happening? P2 is equal to P1 or not? So, this is your P1 to start with, initial, right, but P2 is here. So, therefore, P2 is same as the P1 because the same line, no, straight line. Okay. That means this expression, the V1, then what it will be? V1 will be 0, right. So, therefore, it is basically, if it is 0, then what will be V2 then? V2 also will be 0, yes or no, right. Why? Because V2 square we can write down P2 minus P1 rho 2 by rho 1 minus 1, right. So, which is not possible, yes or no? Is it possible? No, na. So, similarly, if you look at point A, what it would be? Point A, M1, because point A, what happened? Rho 1 is equal to rho 2, yes or no? Because the same point, na, right, the rho 1 and rho 2, this is corresponding to what? This point corresponding to rho 2, right, and this is corresponding to rho 1. So, both are same. So, therefore, V1 will be infinity. So, also M1 will be infinity, and what will be the M2? M2 will be also infinity, yes or no? So, therefore, this is not possible. That means, in between it will be impossible. Of course, there is another way of also looking at, you will find out this will be negative, you know, the square. So, therefore, it cannot be. So, this is not possible. That means, only this region is possible. If you look at here, what is happening? P2 in this case anywhere, here what is happening? At this point P2 is very high values, let us say this point somewhere, P2 is very high values. So, you can say that when P2 is tending towards infinity, what will happen to V2 or what happened to V1? V1 also will be tending towards infinity for a particular finite density, right. If V1 P2 is, then means V1 will be tending towards infinity, where this region, right, because this is very high values as compared to P1, are you getting? So, therefore, that also will be infinity, and in the similar way you can say at this region like P2 will be very small, right, and you can also find out that this will be very low velocities, very P2 when is tending towards, or rather I can put other way around arguments, right, that is in this case what is happening, rho 2 or the rho 2 is tending towards what, very larger value, means rho 2 is tending towards very small, rho 2 is tending towards 0, this side, yes or no? This side 1 by rho 2 is very high value, 1 by rho 2 is tending towards infinity, means what, rho 2 is 0, tending towards 0, right. If it is there, then what will happen to V1? Rho 2 is infinity, right. That means if it is, this will be 0. So, there will be some finite values, right, that means rho 1 will be having some velocity and P2 is also smaller, right, it is going towards that. So, that V1 will be smaller, right. So, V or M1 will be tending towards smaller, means tending towards 0, and M2 tending towards infinity, which is really not possible, because you cannot have M1 is 0 and the M2 will be in very high values, it is not possible. So, therefore, certain region it is not really possible, right. So, this will be not will be considered. So, what we will do now, we will be looking at basically a Rayleigh relationship now by considering relation we can get minus P1 1 over rho 1 minus 1 over rho 2. So, if I plot this thing P2 versus from this relationship, I can have basically plot P2 versus the 1 over rho 2 for a particular value of mass flux rate for a fixed mass flux rate P2 versus 1 by rho 2, what it would be? It will basically a straight line, is not it? Yes or no? It is a linear, right. So, therefore, what I will say, if I will, and it will be trying to intersect this Hugonoid curve, this is known as Hugonoid curve, right, because this is we have discussed from the Rankine Hugonoid curves, right. So, if I will do that, what will it will start from here, right, and it will be a straight line, right, it will be kind of things, and this line is known as Rayleigh line, and this point whichever will be tangent, this will be tangent to the Hugonoid curve, that is known as the upper, this is the upper one, there is a lower upper one here, we call this as a upper Chapman-Joget line point. This is known as basically in short form you can say the Cj. Similarly, there will be another point here which is known as lower Cj point. Cj means Chapman-Joget point, right, and this will be having a velocity, right, which will be corresponding to the this Hugonoid curve, and keep in mind that this will be very high velocity, this is detonation and this is this portion from here to there, that region is known as the deflagration. And keep in mind that this in the normal shock wave generally this portion will be not possible due to the violation of second law of thermodynamics. And because the entropy will be decreasing, lower branch is not possible. And what we will be looking at now, we will be looking at this portion from A to this region and B to this region, and see that where it will be possible, and various regime we will be discussing about. So, as I told, just to make it very clear, that when you this Hugonite curves being plotted P 2 versus 1 over rho 2, you will get that this curve which I had marked in the last slide as a and this is your B, right, and this portion is physically impossible, right, and this line is basically the Rayleigh line, and as I told that there will be various regimes here, the regime 1, regime 2, regime 3, regime 4 and regime 5, and this portion is known as from this point, because there is the tangent point x between the Hugonite curve and the Rayleigh line, is basically known as the upper Chapman-Joget point, and from here onwards is a strong detonation, which is not really possible in nature, whereas the weak detonation from A to this region, and from B to Y is the weak deflagration, and Y to L, right, this region, right, that is Y to kind of you can say that maybe N, and this I can say is M, right, Y to N is the strong deflagrations. Let us look at the region 1. In the region 1, what is happen is the P2 is far greater than the PU, and PU is corresponding to this point, like if it is, let us say, very very high, right, because this is this point I can call as basically PU. And in this case, what is happening, because 1 by rho 2 will be less than 1 by rho 1. That means what? That means rho 2 is greater than rho 1, yes or no, right? Rho 2 is greater than the rho 1, and if it is case, then you can look at what is happening to Mach number M1, 1 by gamma P2 by P1 minus 1 by 1 minus rho 1 by rho 2. So, if you look at, basically this rho 2 is much higher than the rho 1, therefore, this will be very small, this may be tending towards 0 if it is very very high, right. So, therefore, what happened, the Mach number will be very high, M1, and what happened to M2, this is square, okay, M2 square is 1 over gamma and 1 minus P1 by P2 . So, M2 square also will be very, rho 2 is very high as compared to rho 1. So, therefore, it will be also very high values, and P2 of course is a very high values as compared to P1. So, therefore, it will be 1, I am like it will be higher values. So, gas velocity related to well front is slowed to the subsonic speed, and pressure density increases significantly, that means P2 rho 2, right, M1 tending towards rarely observed, you cannot really get the m1, the inlet velocity is being so high, very infinite towards end. I am talking about here in this region, from that onwards, right. So, therefore, it is basically not possible to have this region, right, really observed. And region 2, this portion, if you look at the pressure P2 is less than the pressure of Cj, the detonation point Pu, and which is of course the weak detonation region. And the gas velocity related to wave front is slow to the subsonic speed in this region. So, therefore, it is really possible, and the burnt gas velocity is greater than the speed of sound at isochoric process, because isochoric means what? The density is almost same as that in this region, like if you look at in this region, basically density is approximately same as that. So, therefore, it is possible, but here it is going up very kind of things higher, and weak detonation attains under these conditions that attains a infinity velocity. So, therefore, this is not possible as we had seen earlier. Region 3, in this region is P2 less than P1, because P2, if you look at in this region, P1 is here, this will be P2 should be greater than P1, and therefore, the density 1 by rho 2 is here in this region. Actually, there is a rho 1, and 1 by rho 2 is greater than 1 by rho 1. In this region, it will be higher, right. And therefore, as I tell m1 in this region imaginary, because if you look at this case, rho 2 is smaller. If it is smaller, this will be very higher values as compared to 1. So, therefore, it is imaginary or physically impossible. So, region 4, so this is if you look at in between, what is happening in this region, the P2 is lying between PL, this is corresponding to PL, right, this correspond to PL, and also the P1 is corresponding to this one, right, this portion. And gas velocity related to wave front is accelerated, right, and as a result, what will happen, this isobaric, because process which will be taking place in this region, there will not be much change in the pressure. If you look at between this and this region, the pressure will not be changing much, right, although the P2 is less than P2 is less than P1, and the difference P2 minus P1 is quite small. So, therefore, it will be really possible to have the deflagration, weak deflagration occurs. The region in this case, what is happening, the density 1 over rho 2 is far greater than the rho 1 in this region, from here to this strong wave which will be taking place in this region, right, and whereas the P2 is very less than the P1, because P1 is here and P2 is very less. So, as a result, what will happen, the M1 is quite small, right, and M1, M2 will be quite large, which is impossible, which is not possible or not never possible in practice. Therefore, the strong deflagration is never possible in practice. Why? Because if the flow is subsonic, like the initial state, and then you cannot have a supersonic flow without the formation of any shock wave. So, therefore, this is not really possible, and the strong deflagration is impossible to occur in nature. And keep in mind that we will be basically discussing about the weak deflagration. That means, the premixed flame is basically will be weak deflagration between this region. Actually, this is not possible. So, in between this region, which we will be discussing about. Similarly, the weak detonation is possible, and whereas the strong detonation is not possible. Let me give you some values what is happening in case of deflagration and detonation. If you look at V1 C1, this is nothing but your what? Your Mach number 1 is very, very low, whereas the detonation it will be 5 to 10, it is very high. Unless it is beyond 4 or something, detonation won't occur, right. And V2 by V1 is 4 to 6, whereas it is other way around, that is 0.4 to 0.7, just opposite of that. And P2 by P1 is 0.98, it is almost negligibly small, you can say it is not changing, 1, approximately equal to 1. And whereas here the pressure is 15 to 55, kind of very high pressure across the combustion wave. And T to T1 is 4 to 16, whereas here it is much higher level. And density of course is a small change, but here it is other way around, it is much higher, 1.2276. So, this is the range I am giving, so that you can see it is just opposite behavior you can see between the deflagration and detonation leads to the explosion, and one has to avoid that. Of course, nowadays people are talking about pulse detonation engine, using the detonation as an energy source, or enhancing the combustion process and then reduce the emission and also have an engine, but it gives a lot of noise, and that is a bigger hurdles for the development of pulse detonation engine. Thank you very much. We will take up an example in the next lecture to discuss about how to handle this detonation and deflagration in that. Thank you very much.